Well, good morning, chemistry students. Hey, it's Thursday, 4/23/20. Time to start a new chapter. So, we're going to be going into chapter 8 on covalent bonding today. Okay, and we're going to compare that. This is definitely going to blend right in with the last chapter where we talked about ionic bonding and metallic bonding. The textbook that I used years ago had all of it in one chapter, and that was huge. And you might be saying to yourself, well, that chapter 7 didn't seem too bad with the ionic and metallic bonding. Turns out that there's a lot of stuff on covalent bonding. So this chapter is a lot deeper, a lot more rich than the last one was. All right, so some learning targets for today. This will be a fairly short basic lesson, I think. One, I can use electronegativity to predict the type of bond likely to occur between two atoms. Electronegativity is really going to be a key. A couple basic definitions. You should be able to define covalent bonding and define molecules. And when we look at formulas, I can understand information given in molecular formulas and structural formulas. So some basic targets for today. There we go. So let's review that definition of electronegativity. Okay? Electronegativity is the ability of an atom in a compound to attract electrons towards itself. So picture two atoms and they're bonding together. And so something is happening with their valence electrons. There's some sort of attraction. Now, electronegativity says the atom wants to draw the electrons towards itself. So when we had ionic bonding, what we had was situations where one atom really had a strong electronegativity, was pulling electrons towards it. The other atom had a very low electronegativity, and so wasn't pulling electrons towards it. And as a result, we had this transfer, this takeaway. Well, that's not the only situation that can happen. What if both atoms have a strong electronegativity? Now what happens? So remember our trend on the periodic table, electronegativity it increases as we go up and to the right across our table. The most electronegative element on the planet is fluorine. So remember that last column of the table, the noble gases, they've got their outermost energy level completely filled with electrons. They don't want any more, they don't want any less. So our trend doesn't really fit into that. On the opposite corner of the table, if we could actually have a sample of francium, which we really can't. Francium is one of the most rare elements on the planet because it's highly radioactive. And so whenever an atom of francium is produced by the radioactive decay of other atoms, very quickly it decays again into something else. And so there's never very much francium on the planet. But if we had some francium, it would likely be the least electronegative element on the planet, with electronegativity around 0.7, maybe 0.6. So there's our difference. So let's think about our table. And you know that we've got metals and we've got nonmetals. And metals tend to have low electronegativity, and nonmetals tend to have high electronegativity. So in the last chapter, if we put a metal together with a nonmetal, opposite sides of the table, there's a big difference in electronegativity, and so we got a transfer, and we got ionic bonding. Okay? And then we looked at, well, what happens if we have two metals? And so neither of the atoms has very strong attraction for electrons, and that's where the electrons just are kind of able to drift from atom to atom, the mobile electron, see, that we had in a metallic bond. All right, what if both atoms are nonmetals? Both are over on this table, maybe nonmetals and metalloids. They both have a relatively strong attraction for electrons. So now it's like neither atom wants to let go of the electrons. We got to think about what that's going to do for our bonding. But that's where we're going to be getting into covalent bonding. So just looking at the table, if you had a metal and a non-metal, my first thought in my head is that's going to lean towards ionic. If I have two metals, metallic bonding, and if I have two non-metals or maybe non-metals and metalloids, I'm thinking covalent bonding. Okay, that's a real good rule of thumb for starters. We're going to see that bonding is really a continuum where ionic is one side and covalent's the other side, and there's everything in between, and so a lot of these things are going to fall somewhere in between. You know, is it purely ionic or purely covalent? No, it's kind of a blend of the two, but you know, we humans don't like that. We like to categorize things. So from a thinking standpoint, metal and non-metal, best to start out with the idea of ionic. All right, so let's just look at a couple. What if I said we're going to form a bond between chromium and iron? These two blue shaded ones here. Well, hopefully you're looking at it and saying, well, they're both metals. Neither one's going to have a strong attraction for electrons. That must be metallic bonding. What if we had a bond between calcium and oxygen? Well, calcium's way over here on the metal side. In fact, it's way over as active metal. Oxygen is a very active non-metal. So low electronegativity, high electronegativity. It's probably going to be that transfer of electrons. We got ionic bonding. What if we made a bond between carbon and chlorine? Well, both of these have a reasonably high electronegativity, a reasonable attraction for electrons, and so neither one wants to let go. And we're going to have to get into what happens when they don't let go. But the answer is a covalent bond. So what is a covalent bond? It's a shared pair of electrons. Okay? All right. So this would be a better demonstration if I had someone to help me out, which I always do in class. But I'll pick somebody in class. Oh, pick me, pick me. Okay, Kevin. All right. Here's your valence electron. You have this one valence electron that you're not really very attracted to. Okay? And so then I need another volunteer. Oh, pick me, pick me. All right, Mr. Rupp. You're going to be a non-metal. And non-metals really want another electron. So what happens if we bring these two together? So Kevin's over here with this valence electron. You know, it's all right. It's nothing great. And Mr. Rupp's over here. He really wants another electron. And so when Mr. Rupp sees this extra electron, he's like, hey, give me that. Well, that was an ionic bond. Well, okay, what happens if we have two Mr. Rupps? So, I've got some electrons, but I really want another one. And I've got some electrons, but I really want another one. And so what if the two come together, and this guy tries to take the electron from him, and this guy tries to take the electron from him? I'm sorry, I'm feeling like I'm getting a multiple personality disorder here. But the two, they both try to take the electrons from the other, and they're stuck. They're stuck together because they both want the same electrons. And neither one wants to let go, so guess what? They're stuck together. That's a bond. Because they both want the same electrons. You know, imagine you're going to the big Black Friday sale, and what are you shopping for? I don't know, the newest, best iPhone. And you get in the store, and you see the last one, and you reach for it, and you grab hold of it, and at the same time, somebody else reaches for it and grabs hold of it, and you both have the same iPhone in your hands at the same time, and neither one of you wants to let go. And so now, you know, you're struggling over it. You got your tug of war over it. It's really kind of interesting when we look at the language. We say a covalent bond is a shared pair of electrons. So you got the two atoms. This one's holding on to electrons. This one's holding on to electrons, and we say they're sharing. I don't really see sharing. I see there is a tug of war. There's a battle going on, and neither one wants to let go, so they're stuck together. It's not like a cooperation taking place, but it's what neither one wants to let go. So they're stuck together. They're bonded. So a covalent bond literally is a shared pair of electrons. So we might also say covalent bonding is a type of bond in which two electrons are shared between two atoms. Okay? Now, remember in metallic bonding, we said that the electrons are shared, but remember, in that case, the electrons weren't locked up in place. They were free to move all around the metal structure. They were shared by all the atoms. Here we're saying, no, it's between two atoms. Two atoms are both grabbed hold of the same electrons. Those electrons are locked up. And the atoms are therefore locked together. So, a molecule is a neutral group, so neutral means no charge, of covalently bonded atoms. Anytime you have a group of atoms that are covalently bonded to each other, turns out that group can kind of exist independently from everything else. So whenever we have a molecule, we know it's covalently bonded. When we use the adjective molecular, molecular really means the same thing as covalent. So if I refer to a molecular substance, I'm also referring to a covalent substance. Just to compare, in the last chapter when we talked about ionic bonding, we said we get these ions, positive ions and negative ions, and they're all locked together. Remember, they fit together in the simplest ratio. For every positive, there's a negative. For every negative, there's a positive. But really, the entire crystal is kind of bonded together. In a covalent substance, I'm going to use water. That's the substance that you're probably most familiar with seeing formulas. H2O, two hydrogens, one oxygen. That hydrogen is sharing a pair of electrons with that oxygen, and that hydrogen is also sharing a pair of electrons with the oxygen. So each hydrogen has a single bond, and the oxygen has two bonds. But it turns out that that particular group of three atoms is kind of independent of everything else. It's got weaker attractions to its neighbors, but it can exist independently, whereas over here, no, none of these things were independent of each other. We write the formula for sodium chloride as NaCl, but it doesn't really represent one sodium and one chlorine. It's just the ratio. Here, it can actually represent two atoms of hydrogen and one atom of oxygen as a distinct unit. That's a molecule. So a couple of formula types to look at. We have molecular formulas. And so what we have a symbol for the elements, and we have subscripts after the symbol indicating the number of atoms. So it shows us the type of atom and the number of atoms in a molecule. That's what's in a molecular formula. So C2H6O means there's two carbons, 6 hydrogens, 1 oxygen. Sometimes we need more information than that, so we go to a structural formula. Now, in a structural formula, you'll also have the type of atoms, you'll also have the number of atoms, but you also get the arrangement of the atoms. So from that molecular formula, C2H6O, I could arrange those atoms this way, where the oxygen is in the middle, and the 2 carbons are attached to the oxygen, and then there's 6 hydrogens around. Or I could put the carbon bonded to carbon and put the oxygen sticking off of just 1 carbon, and then the hydrogens go around. The same atoms are used here. In both cases, I have 2 carbons, 6 hydrogens, and 1 oxygen. But the different structure actually makes them different compounds. This is ethanol. That's the compound that you find in alcoholic beverages. Much better used for an industrial solvent and things like that. And this is a compound called dimethyl ether. And while this one is somewhat toxic, you certainly wouldn't want to replace it with that one, because that one would be very toxic. So, structure matters. Structural formula gives us that. Okay, I want to remind you about diatomic elements. So, there are 7 diatomic elements that we commonly refer to, and 6 of the 7 on the periodic table are in the shape of a 7. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. And that means whenever they are by themselves, they're not really by themselves, they form little groups of 2. And then hydrogen is the other one. Okay, we're almost done here for today. What I've got is, let's imagine that this is a very simplified diagram of a hydrogen atom. It's got 1 proton in its nucleus, and it's got 1 electron in its electron cloud. And here's another hydrogen atom. It's got 1 proton in its nucleus, 1 electron in its electron cloud. Now, positives and negatives are attracted to each other. So this electron is attracted to the nucleus. This electron is attracted to the nucleus. Think about this nucleus is also attracted to that electron. And this nucleus is attracted to that electron. Those 2 electrons don't like each other, so they repel. And those 2 nuclei don't like each other, so they repel. But we have kind of a tug of war, a battle going on. There's attractions and there's repulsions. And to some extent, the attractions sometimes win out. Okay? So if this nucleus is attracted to that electron and vice versa, let's see if this works. We see these 2 atoms kind of pulling together until they share that pair of electrons. Now effectively there's 2 electrons by this one. Remember, the first energy level can only hold 2 electrons. So if hydrogen comes closer to another electron, it just filled up its valence energy level. And this atom is also closer to 2 electrons now. So they both fill up their valence energy level. And imagine that merging together, and effectively we get a pair of electrons between the 2 nuclei. And the shaded area is kind of trying to represent the shared electron cloud rather than before. But the electrons here are going to spend most of the time in between the 2 atoms. And yeah, that's as far as I wanted to go for today. So feel free to watch it over and over and over. See you again tomorrow. Be safe.